In chapter 6, we will look into continuous random variables and their probability distributions. A continuous random variable take outcomes that of any numerical value in an interval, including numbers with decimal points. The probability that a continuous random variable equals a specific value is always equal to 0. Unlike the discrete variables that we looked at the previous chapter, the continuous variable can take any value in an interval or collection of intervals. That means, in theory, it could take an infinite number of possible outcomes. And this is why the probability that a random variable equals to a specific value is 0 is because basically it's going to be 1 over infinity. Now, the normal distribution, a normal probability distribution has the following characteristics, is one of the most popular probability distributions for a continuous random variable. The distribution is bell-shaped and symmetric about the mean. Because of the fact that the distribution is symmetrical, the mean, the median are the same. Random variables around the mean where the curve is the tallest have the higher likelihood of occurring than values towards the end of the distribution where the curve is lower. The total area, and this is something that you always have to keep in mind, the total area under the curve is always equal to 1. Because the distribution is symmetrical around the mean, the area to the left of the mean equals to 0.5, as does the area to the right of the mean. So basically, the mean separates the normal curve into two equal parts of 0.5 and 0.5. The left and the right ends of the distribution extend indefinitely, never quite touching the horizontal axis. A smaller standard deviation results in a skinnier curve that's tighter and taller around the mean. A larger standard deviation makes for a fatter, if we can say, curve that's more spread out and not as tall. The formula for the normal probability density function is the following. To find the area of the bell curve, we can use calculus or check the values in the chart that we will be doing. The chart is given on the next page, and it's also available in MyMathLab. If you go to MyMathLab menu charts, you will see the Z chart. This is basically what you are looking for. This is going to be the chart that we will be using for normal distribution. So I would highly recommend that you print this out and you have it next to you every time you do a problem for this chapter. Now, to calculate the probability, we will first need to find the z-score. The z-score determines the number of standard deviations that the particular value x is from the mean. Sometimes you will end up with a negative z-score, other times with a positive z-score. The sign typically indicates whether the value is above, that's going to give you a positive z-score, or below the mean, that's going to give you a negative z-score. In general, the z-scores follow a normal distribution with mu equal to 0 and sigma equal to 1. A standard normal distribution has mu equal to 0, sigma equal to 1. The z-score for a normal distribution are negative for values of x that are less than the distribution mean, as we mentioned before, positive for values of x that are more than the distribution mean, and 0 if the mean and the value are the same, basically, number. Now, how do we calculate the probabilities based on the z-scores? The first step is to read the probability of the z-score in the chart table of page 2. Use the row for the first decimal unit and the column for the second decimal unit. So, when you look at your table, let's see how we're going to be reading it. Two things that I want you to focus on when you look at this table. First of all, I want you to pay attention to what area this table gives you. That means when you look at your normal curve, always remember that whatever number, whatever probability you get from this table will always be the area from the mean to your z-score. All right, from the mean to the z-score. If you have a negative z-score, it will be the same on the other side. and obviously the probabilities are always positive. So first thing, whatever, once again, you get, whatever number you get from this table will always be the area from the mean to the z-score that you have calculated. Let's say that you calculated the z-score to be equal to 1.65. You will first read the table going down and then across. So 1.65, you're going to go to 1.6 right here, and then you're going to move across to find 0.5. So you can make 1.65. 0.5 on the top. Where do these two meet? Right here, 0.4505. So this will be the probability that will correspond to a z-score of 1.65. Let's say you had a z-score of 0.77. You would go right here for 0.7, and then you would move across to 0.7 to find the corresponding probability, which would be 0.2794. So this is basically how you read your table. You can highlight these two lines here to make things a bit easier. Now, let's say we want to calculate the probability when the z-score is between 0 and a positive number, or 0 and a negative number. In this case, you check the table of the norm distribution, and the answer, the probability, will be given directly from the chart. That means whenever we talk about areas, we talk about the corresponding probabilities. So we talk in terms of areas for the corresponding probabilities. So whenever you're looking for an area that's between 0 and a specific z-score, the answer will be whatever you get in your table. Why? Because this is exactly the area that your table gives you. For example, let's look at this example. We want to calculate the probability where the z-score is between 0 and 1.77. Keep in mind, for these problems, you already have standard normal distribution, which means you don't need to calculate the z-score. You already have the z-score. So the mu is equal to 0, and you want to know the area between 0 and 1.77. 1.77 is positive, so the area will be to the right. So you will go to your table, and you will go 1.7, and then you will move across to 0.7, 0.4616. So the answer will be 0.4616. So this area here that we are looking for is 0.4616. Now, calculate the probability where the z-score will be between 0 and negative 2.15. Negative 2.15 will be to the left of the mean being 0. So I'm looking for this area from 0 to negative 2.15. You will take the absolute value, given the table that we use. Even if you have a negative z-score, it will still be the same table. You simply take the absolute value. So you check for 2.15, so you're going to go 2.1, and then you will move across to 0.5, so 0.4842. So the answer will be 0.4842. You do not need to make any adjustments. This is the area that your table gives you. So this is your answer. Even if you have a negative z-score, the probability is always positive. Keep that in mind. The probability is always positive. Now, in the case where you are looking for a tail, and what do we call tails? We call tails the ends of the normal curve. So whenever you're looking for the ends, either to the left or to the right, you will always find your z-score. If you have your z-score, you will check it on your table. The table will give you this area. You are looking for this area. So you will take whatever you get from the table and you will subtract it from 0.5. Let's look at this example. I'm looking for the probability where the z-score is greater than 1.85. 1.85 is to the right of the mean since it's positive. I'm looking for the area that's greater than 1.85. That means I'm looking for this area right here, as we call it the tail. Next step, you check your table. 1.85, 1.8 across for 05 is 0.4678. However, this is not your answer, right? This is not your answer. 0.4678 will be the area from the mean to 1.85, so this area. However, you're looking for this area. We know that this right here, this part right here is 0.5, right? The mean separates a normal curve into two equal parts of 0.5 and 0.5. So you will take the area that you know right here and you will subtract it from 0.5 in order to find the area that you're looking for. If we do so, we will see that the probability that the z-score is greater than 1.5 will be 0.0322. Same thing with the other side. I'm looking for the area where the z-score is less than negative 0.75. We will check the absolute value 0.75, which is 0.2734. 0.2734 is this area from the mean to the z-score. I'm looking for this area, however. I know that this part here is 0.5. You will do 0.5 minus 0.2734, and your answer will be 0.2266. So always remember, when you're looking for a tail, and again, tail are the ends of your normal curve, you will always do 0.5 minus whatever probability you get from the table. Let's see now what happens when I'm looking for an area between two values, between a positive and a negative z-score, which means that in this case, the mean is inside the area you're looking for. So if you are looking for the area between negative, let's say 2.5 and positive 1.5, then this will be the area that you want. All you need to do is check your table for 1.5 and then for 2.5. So 1.5, it's going to be 0.4332, right? 0.4332. 2.5 is going to be 0.4938. 0.4938. So we have this area and this area. I want the whole thing. So all I need to do is add the corresponding probabilities that I get from the table. So as a rule, if you're looking for an area between two values where the mean is inside that area, as you can see here, or if you're looking for an area between a positive and a negative z-score where the mean will be in the middle, then check the corresponding probabilities for each z-score, and then whatever you get from the table, you add them. Now, what happens when I'm looking for an area between two positive z-scores or two negative z-scores? Or what happens when you're looking for an area between two values where the mean is outside that area? Pay attention. The mean is outside the area you are looking for. In this case, you will check your table for the first z-score, the probability for the second z-score, and then you will subtract the corresponding probabilities. And let's see why. Let's look at this example. Calculate the probability where the z-score is between negative 2.75 and 1.65. So negative 1.65 is here, negative 2.75 is there. I'm looking for the area between these two values. I will check, I will take the absolute value and I will check for 1.65. That will give me this area right here, and then I will check for 2.75. That will give me this area. Keep in mind, From the table that we use, you always get the area from the mean to the z-score. All right, so for 1.65, we get 0.4505, and for 2.75, we get 0.4970. And therefore, we will need to subtract it in order to get the area that we are looking for. So keep in mind, whenever you are looking for an area between two negative z-scores or two positive z-scores, and the mean is outside, if you notice in both cases, then in this case, you know that you will be subtracting the probabilities from your table. And here we have the table that kind of summarizes the rules when it comes to the areas you're looking for. So please make sure that you understand this table. Now, to get to the table, however, when you are given a problem, you will be given a problem where you will have a normal distribution with specific characteristics. You will be given mu, you will be given sigma, and then you will be asked to find a specific probability. In doing so, the first step you will do is write down the probability you're looking for, then calculate the z-score. When you write down the probability you're looking for, draw the normal curve, check the areas that you're looking for, calculate the z-score, and then check your table for the corresponding probability. So let's look at this example. A company that sells annuities must base the annual payout of the probability distribution of the length of life of the participants in the plan. Suppose the probability distribution of the lifetimes of the participants is approximately normally distributed with a mean mu equal to 68 and a standard deviation equal to 4. What proportion of the plan recipients would receive payments beyond age 75? So I'm looking for the probability that X is greater than 75. Now, to do so, I first graph the normal curve. Mu is 68. 75 is to the right of the mean because it's greater than the mean. I'm looking for the probability where X is greater than 75, so I'm looking for a tail. To use the table, I first need to calculate the z-score. The z-score is X minus mu over sigma, 75 minus 68 over 4, 1.75. Then you go to your table for 1.75, 0.4599, which is this area right here. However, this is not the area that I'm looking for. I'm looking for a tail. I know that this part is 0.5, so you will do 0.4599 minus 0.5, and your answer will be right here. Now, for the second example, we know that the length of time it takes a college student to find a parking spot it follows the normal distribution with a mean of 3.5 minutes. So we have mu equal to 3.5, standard deviation sigma equal to 1. Find the probability that a randomly selected college student will take between 2 to 4.5 minutes to find a parking spot. So I'm looking for this probability. I have two values. I will need to calculate two z-scores. One z-score for 2 and another score for a z-score for 4.5. We do our calculations and we get negative 1.5 and 1. By doing these calculations, I just want to show you something. Basically, you're turning this normal distribution into a standard normal distribution with mu equal to 0, with a z-score of negative 1.5 and 1. And I'm looking for this area. These two things are the same. We just have to turn the normal distribution into a standard normal in order to be able to get the corresponding probability from the table. So all you need to do is check your z table for probability of 1.5 and for 1. So this area here is 0.3413 and this area is 0.4332. Since I'm looking for this whole thing here, I simply add the corresponding probabilities. Whenever the mean is inside the area you're looking for, you will be adding the corresponding probabilities. Now, the empirical rule is used for normal distributions. According to the empirical rule, if a distribution follows a bell-shaped symmetrical curve centered around the mean distribution, then approximately 68%, 95%, and 99.7% of the values will fall within 1, 2, and 3 standard deviations above and below the mean respectively, which means 68%, 68.2% of the data will be between mu plus minus 1 standard deviation. 95.4% of the data will be between mu plus minus 2 standard deviations from the mean, and 99.7% of the data will be between 3 standard deviations from the mean. This is basically what the empirical rule states. So let's look at an example how we apply the empirical rule. The amount of time that students spend on Instagram follows the normal distribution with a mean of 65 minutes, standard deviation of 8. The time that 95.4% of the students spent on Instagram is between which 2 values? You know you have normal distribution. You are looking for approximately 95% of the values, so that means that we are using the empirical rule. 95% means 2 standard deviations from the mean. So mu plus minus 2 standard deviations, we have 65 plus minus 2 times 8. 2 times 8. So you will have 65 minus 16 for the lower limit, 65 plus 16 for the upper limit. So you would say that approximately 95% of the students spends between 49 to 81 minutes on Instagram. Now let's move on to exponential distribution. The exponential distribution is the continuous counterpart of the discrete Poisson distribution from the previous chapter. The graph of the exponential distribution is skewed to the right. For example, if a random variable follows the exponential distribution with an average time between arrivals of 5 minutes, lambda is equal to 5, then the same random variable also follows the Poisson distribution with a mean of 0.2 customers per minute, so your lambda would have been 0.2. The formulas for the exponential cumulative distribution are as follows. If you know that you have exponential distribution and you're looking for the area where x is less than or equal to a specific value, you will always do 1 minus e raised to the negative power of x over lambda. If you're looking for an area where x is greater than a specific value, then you calculate this probability by simply taking e raised to, I don't know if you can see it clearly, negative power of x over lambda. And then if you're looking for an area between 2 values, so basically when you have, just to kind of explain it a bit more, when you have your exponential distribution, this is what how it would look like. So the only thing given to you would be your average. So there's really no ending to your distribution. So if you're looking for an area that's greater than a specific value, then you will always do e raised to the negative power of x over lambda. If you're looking for area that is less than, you will be doing 1 minus e raised to the negative power of x over lambda. And if you are looking for an area between two values, you will either find the area that's greater than x1, and then you would subtract the area that's greater than x2, or the other way around. You would find the area that is less than x2, and you would subtract the area that is less than x1. That's basically how you need to do it if you have an area between two values and you have exponential distribution. So let's look at some examples to make things a bit more clear. Time spent watching TV every week by first graders follows an exponential distribution with a mean of 10 hours. What is the probability that a given first grader spends between 10 and 15 hours watching TV? So we have exponential distribution with lambda or mu equal to 10. We want to calculate the probability that x is between 10 and 15. All right, so we find the area that is less than 15. Less than 15 is this calculation right here, minus, and then we subtract from that the area that's less than 10, which is this area right here. Now, if you want to, when you use your graphing calculator for exponential, let me just show you. You want to go second E right here. Let me show you here a bit better. You want to go to second, let me just, second ln. Second, and then you go ln right here, second ln, and then for the negative sign you want to go next to the point right here. This will be your negative sign, not the minus sign. You want to use the negative sign right here. Now, for the other example here, what is the probability that a given first grader spends less than 14? Let me just zoom it back in. Less than 14 is 1 minus e to the raised to the negative power of x over lambda. So you would do 1 minus second ln to the negative power of 14 over 10, and you get 0.7534. And the next distribution we're going to look at is the uniform distribution. It is a simple type of continuous probability distribution. Since it is continuous, it has a graph, and the area of the graph is the probability. The graph for a uniform probability is rectangular. With a continuous uniform distribution, the probability of any interval in the distribution is equal to any other interval with the same width. The formula for the uniform cumulative distribution is the following. When you're looking for an area where, let me just zoom in a little bit, you're looking for an area between two values, you will take x2 minus x1 over b minus a. The mean and the variance of the standard, the mean and the variance and the standard deviation of the continuous uniform distribution are as follows. If we're looking for the average, we will get the starting point plus the ending point divided by 2. The variance, the ending point minus the beginning point squared or divided by 12. And for the standard deviation, we simply take the square root of that. So basically, b minus a over the square root of 12. So let's look at this example. Let's look at this example. Suppose the time interval between two consecutive defective light bulbs from a production line has a uniform distribution of an interval from 0 to 90. So this is your 0 to 90. What is the mean? The variance and the standard deviation of the interval. We said that the mu is A plus B divided by 2. So 0 plus 90 divided by 2, 45. The variance, 90 minus 0 square over 12, 675. And then the square root of 675 for the standard deviation, 25.981. What is the probability that the time interval between two consecutive defective light bulbs will be less than 10 minutes? Less than 10 minutes is the area to the left of 10. That means you will take the ending minus the beginning of the area you're looking for, so 10 minus 0, and you will divide it by the end point minus the beginning point of the distribution. So 10 minus 0 over 90 minus 0.111. What is the probability that the time interval between two consecutive defective light bulbs will be between 10 and 35? So now I'm looking for an area within the limits of your uniform distribution. So all you need to do in cases like this is subtract the end point from the beginning point of the area you're looking for over the end point minus the beginning point of your distribution. So therefore 35 minus 10 over 90 minus 0, and the probability will be 0.2778. And this concludes the notes for chapter 6.